Okay, welcome everybody. Today is our fourth meeting. So before we start, I wanted to briefly let you know of a couple of things I've done. First of all, on Canvas, I've added in quizzes an anonymous forum. So unfortunately, Canvas does not have still yet an anonymous forum. But you can kind of work around that by creating a quiz that is ungraded, obviously anonymous, whatever. So try to use that. If you have any question, try to put it there. We'll see how it goes. I've never used this before, so let's try to use this feature. And another thing I wanted to mention is, what else I wanted to mention? Initially, I was not planning to do this, but as you can see, I'm using, these are my personal notes that I use for the lecture, and probably you've seen on the post-lecture video that I use. Nobody still asked me if I wanted to. I'm taking that my handwriting is horrible. But in case you wanted to, I'm happy to give my lecture notes as they are. Don't ask me to do any modifications to them, but still are a good representation of what I do here. So if you think this is useful, I can post them together with the lecture and all the. Is that going to be useful? Yeah. Okay. So I can put this. And what about the staff student forum? Did you mention the issue?
The general gist is, they're being a bit silly, but it doesn't seem like there's much anyone can actually do.
All right. But this was minuted anyway.
Yes.
Okay. So can you please let me know? I'm not sure if I will be informed when the minutes go out. So let me know when. So they've already been published?
No.
Okay. Yeah, please, yeah. So we can see if we can do anything about that. Okay, and there is something else I wanted to mention, but is there any other business we wanted to discuss? For now, no. Oh, this is one thing I wanted to mention. I don't want to spend too many minutes. I'm always in a rush. I was thinking of, normally you would have tutorials at the end, which we will have, But I was thinking of also adding some tutorials as we go. Is this something you may find useful? I can try to organize. This will be extra. I won't be using the lecture time for that. It will be extra, I don't know, 2 hours, I don't know, next week, or we'll do it 2 or 3 times, I don't know, to try and do some exercises. But please try to use the quizzes that I post, because these are very good representation of the exam questions. So try to look very well at the quizzes that I post every week. Okay, let's move on. So if somebody, I'm sure somebody of you may have questions to ask. Can you try and use this forum here? And we can see if, it should be anonymous, so you can ask anything also, how's the weather? But I want to see how it works. I don't know on my side how I can reply or, these things. So we can use this efficiently, because obviously the questions of one are the questions of everybody. So that's why I think this is useful. Okay, and so yeah, these are my notes, as you can see. This is what we will be doing today. And actually, I will start from here. So today we are going to discuss an important concept related to, today we are finishing semiconductors. Most of these things are things that you've already done in a way. Probably, I'm not sure you've done generation recombination. So today we will discuss generation recombination, and then also what does light, how light interacts with the semiconductor and what it does, absorption, emission, so on. So let's start with generation and recombination of carriers in a semiconductor. So we've said that in a semiconductor there is a thermodynamic equilibrium. And last week, what we've said is that in any semiconductor, whatever the semiconductor is, doesn't matter if it is intrinsic, extrinsic, whatever, and time t is equal to I squared. That is true forever, when it is at thermodynamic equilibrium. Now, there are obviously situations where the system is brought out of equilibrium. In the post-lecture video of last week, I've briefly analyzed, what it means when the system goes out of equilibrium. Basically, what happens is that NT becomes different from Ni squared. Okay, so probably you have had a look already at that. So this equilibrium is a thermodynamic equilibrium. It's a dynamic equilibrium, which means at any moment in time, there is a constant generating and recombinating of carriers. So overall, at any time, n time p is Ni squared, but is dynamic. That means that carriers disappears, carrier appear. And that's what this little diagram here is trying to show you. So say that at a certain point in my semiconductor, I have 3 electrons in the conduction band, and so 3 holes in the valence band. Let's assume that this is an intrinsic semiconductor. At time t1, the system is in thermodynamic equilibrium. So this means that after some time, there will still be a total of 3. But it's different 3. I've named them 1, 2, 3, 4, 5, whatever. I've tried to name the electrons, if you like, as weird as it may sound. But as you can see, at any time, it will be different, the electron or the holes that are up there. But in total, the number is always the same. That's what it means that the system is in equilibrium. Okay, now, there are, though, processes and events that may bring the system out of equilibrium. So, let me remove this so that you don't get confused. Oh, sorry, you were copying? Yeah, I'll leave it on then. So, we have then 2 processes to deal with. Generation of electron-hole pairs, and the recombination. These are the 2 pillars that keep the system in equilibrium. And if the system goes out of equilibrium, these 2 processes make sure that the system is brought back into equilibrium. So these 2 processes are capable of re-establishing the equilibrium. So regarding generation, well, who can generate carriers? We know already that temperature is embedded into the theory of semiconductor as something that can generate carriers, isn't it? We've seen it last week, that electrons, due to temperature, can be promoted into the conduction band. So this is a generation process. I'm generating electrons and holes. So I want to discuss temperature here. It's already embedded in the equation of semiconductors. But one way we can generate electrons and holes is through light. So electromagnetic waves. They can, through photoelectric effect in the end, absorption of photons. So let's say that one thing we will deal with is that generation through light. Now, regarding instead recombination, well, there are several different processes that can be important. The first major differentiation that we have to do is that during recombination, what we do is that the electron and the hole recombine. There is a lot of energy there at play, so this energy has to go somewhere. This can be transformed into a photon, so recombination can be radiative, or non-radiative, where basically the energy is dissipated into heat in the end, through, for example, scattering into the crystal. So radiative, non-radiative processes. And in the end, the processes that take place during recombination are very, very much dependent on the fact whether the semiconductor is direct or indirect. Do you remember last week we saw this definition? What it means that a semiconductor is direct or indirect. It has to do with the position of the bottommost point of the conduction band and the topmost point of the valence band, if they match in K or not. We will come back to this later anyway. So, and what else? The situation where the system is brought now out of equilibrium is generally the one that we will deal with most is the one where this quantity is actually bigger than that. This situation is called when NP is bigger than Ni squared, so I have effectively more carriers than thermodynamic equilibrium would allow. This is called, obviously, injection of extra carriers. We have introduced more carriers than we should. Now, so if we have more carriers than we should, the system has to look to recombine some of them to try and reestablish equilibrium. So at this point, we can go ahead and try to differentiate the different recombination processes. So we've in a way kind of already said that, but what we can say is that recombination can be of two kinds. So recombination can be direct, which means a band-to-band process. It's exactly what you might have already in mind, where the electron from the conduction band and the hole from the valence band recombine. That's what is called direct recombination. Band-to-band recombination also is called. Band-to-band. Now, this process dominates in mainly indirect semiconductors. Now, the other process is obviously indirect. Indirect means that there is a step in the middle. You know, you have your electron in the conduction band, the hole in the valence band, and they don't recombine directly, but they recombine through a recombination center that is a state, as we've seen last week, the impurities, you know, the dopants, that they appear as states in the band gap. So we can look at impurities that appear quantum mechanically as states in the band gap. So they participate in this indirect recombination process. I have a figure to show you in a moment. So the direct recombination, this is mainly radiative. Mainly radiative. The indirect recombination, as I said, through what we call these impurities, these extra states that appear can be, in general, are defects. So defects can be, imperfections in the crystal, dopants as well. So can be anything that goes beyond the pure crystal will appear as a state into the band gap, and that can work as a recombination center for an indirect recombination, which is non-radiative by definition. Non-radiative. So there the energy will be all dissipated in terms of heat in the end. Now, so the direct recombination is dominating in direct semiconductors. Indirect recombination dominates in indirect semiconductors. And mail is that. So regarding this one here, this class, direct recombination, which we said is mainly radiative. Now here we should clarify this point a little bit better, and I will do that using this image. So here are represented these processes. So there, what we see on the very left is direct recombination. Here we see what is the indirect recombination. As you can see, electron and hole recombine through a state that is caused by a defect that is called general traps that appear in between the defects and so on. So this is not radiative. That one is radiative, as you can see the photon coming out. There is another thing there, as you can notice, the Auger process. So this is in competition with this direct recombination being radiative. So the reality is that when you have direct recombination, not all the photons will be able to escape, if you like. As soon as they are generated, well, maybe they're not even generated, let's put it this way, only a fraction of them, X, will be able to finally be generated. There is actually a portion, 1 minus X, that will undergo the Auger process. I will explain what it is, and which is no radiative. The Auger process is the photon that would have been emitted is actually immediately reabsorbed either by an electron or a hole, and so that photon energy is immediately transformed into kinetic energy of that electron or hole, and then dissipated within the crystal as heat. Okay, that's the Auger absorption, if you like, what I mentioned as Auger process. So intrinsically, there is not 100% of direct recombination events will end up being radiative. Okay, this is just a brief overview of what we are dealing with here. What is that recombination means and the different processes at play. Just because mainly we will be dealing with direct recombination, because this is quite complex, I will probably just mention it for curiosity, but mainly we will be dealing with this. So let's have a look at what direct recombination looks like, both for direct semiconductors and indirect semiconductors. So if I was here to make a plot of, let's consider a direct semiconductor. I will draw the energy band diagram. You remember this word? So the EK diagram. And a direct semiconductor is something like this. This is the valence band, and this is the conduction band, isn't it? So I have, imagine my electron sitting here, and there is a hole there. Direct recombination means this recombining with that, emitting a photon. This is for a direct semiconductor. So direct recombination for a direct semiconductor. For an indirect semiconductor, so this is the valence band, this is the conduction band. So imagine I have my electron here, and my hole there. So here, the transition we are talking about to be direct is this. Okay, we will look at this into the details of the physics of it later on. Okay, so this is for the direct recombination for an indirect semiconductor. Okay, we will look at what this means in detail later on when we talk about light emission, light absorption as well. They are more or less the same. Okay, so let's have a look in detail to direct recombination and see how we can analytically approach this, what is happening. Okay, when my system is clearly out of equilibrium, how we can translate what is happening into some formulas we can use. I will remove. Is it okay if I remove this part? Yeah. Okay, so let's talk about direct recombination. I may have to remove that, but so let us consider an N semiconductor. Remember, we are not specifying whether it is direct semiconductor or indirect. We don't care at the moment. Okay, an N semiconductor. So this means that in thermodynamic equilibrium, we have N0 and P0 carrier densities in such a way that the product of these two is Ni squared. Actually, I will just to clarify the formalism, because I've said I'm using an N semiconductor, I will specify that by adding the subscript N. So N0 means this is the electron density in an N-type semiconductor in equilibrium. Okay, now for some reason, we go out of equilibrium. So I don't have any more N0, I have Nn, which is N0 plus some delta N caused by something. Because of charge neutrality, let's say that this something is light. If light is generating electron-hole pairs, so many electrons, so many holes are generated. So I can already say that Pn is Pn0 plus delta P, where delta P is equal to delta N, because the electron-hole pairs are generated together. So I have to remind myself that delta N is equal to delta P. I've completely destroyed this marker. Okay, until here is easy. Now, there is one more simplification we will do, just because we don't want to do crazy things. So, to keep things simple, we will also assume this is called the low level injection condition. That is, delta N is smaller than Nn0. Injection, we mentioned the word injection previously. When the system goes out of equilibrium due to something, we are injecting carriers. So low-level injection means that this cause that is bringing the system out of equilibrium is at low level. Low level means that the number of carriers that are being generated is still smaller than the majority carrier density. Nn0, remember, this is an N-type semiconductor, so this quantity here represents the majority carrier density. So we are saying, yes, we are creating some carriers, but still they are comparable to the majority carrier density. They're not much more. Okay, and so with this approximation, effectively we can say this means that Nn is roughly Nn0. Just keep it in your mind. This is just for ourselves to remember. But here, in general, remember these are the minority carriers. If you've looked at the examples I've put probably in the post-lecture video, this number generally is small. In an N-type semiconductor, the density of holes is small. But this can be quite big. This can be comparable to that. So this means really that in this whole story, it's this number that is huge. So really it's Pn that is much bigger in general of P0. This is also what we've discussed if you go back to this lecture video of last week, I was talking about the non-equilibrium situation. That's always the end of the story. When the system goes out of equilibrium, what is really changing a lot is the density of the minority carriers. As I'm mentioning, this is effectively related to that. It's the same story. So let's have a look at the generation and recombination now that we are going to analyze. So when the system was in thermal equilibrium, we have a generation process due to thermal processes called GTH that is creating electron hole pairs. And we have, this is in thermal equilibrium, and in thermal equilibrium we have also a recombination process that will, we are talking about direct recombination here, so these are all direct processes, that recombines electron holes. This all at thermal equilibrium. Now, this G and R that I'm introducing here, the generation rate and the recombination rate, are the units of these quantities are, let's say, units of G and the units of R are the same, or 1 over cubic centimeter per second. So they represent the number of generation or recombination events per cubic centimeter, so per volume, per unit time. Remember that N or P, they represent the number of carriers per unit volume. Now, according to that image there, when there is thermal equilibrium, what we can obviously think, we are in thermal equilibrium, this means that that number that will be represented by GTH must be equal to RTH. We can already say that. In thermal equilibrium, this must be true. Furthermore, when the system, we can already anticipate that when the system is out of equilibrium, we've said that processes will try to bring the system back to equilibrium. And we had said that, for example, if NP is bigger than Ni squared, there will be recombination processes that will try to bring down this quantity in such a way that becomes again equal to Ni squared. So we can understand probably that the recombination rate should be proportional probably to this number. The more this number is far from Ni squared, the more they need to recombine fast. The more there is a need for a large recombination rate so that the system goes back to equilibrium. So effectively, what we are saying is that in general, R is proportional, so through a factor, let's call it beta, of N and P. Nn, as we've said here, let's call Nn and then Pn the out of equilibrium values. So we can say in general that the recombination rate is proportional to the product NP through some factor, which will depend from the semiconductor or any other possible factor that could be at play. But we realize from this fact that this must be the case. Yeah? The recombination rate must be related to this quantity, to NP, somehow. So having realized that, we can go on now here. So this was for the in thermodynamic equilibrium. So if this is true anytime, I can say that R in thermodynamic equilibrium is beta N0 P N0. Up until now, I'm just using my head to try and guess, fundamental behaviors here. Okay, but we will see that soon we will reach to a nice conclusion. So from here now, this is in thermodynamic equilibrium, okay, in equilibrium. And this is out of equilibrium now. So let's try to work on this part, having in mind that Nn is this, Pn is that. And also that we've realized that we can write the recombination rate at thermal equilibrium in this way. The reason I'm doing this, the reason I'm explicitly telling you what's the recombination and generation rate at thermodynamic equilibrium is that these are effectively the rates due to temperature. I'm separating now what is caused by temperature. By doing this process, I'm attempting to separate what is caused by temperature and what is something else. G, we said G could be also light. Okay, so that's where I'm going effectively. So you will see in a moment, hopefully. So what we can do this at this point is two things. One, I can substitute this stuff in here and realize that, you see, based on what we've just said, that effectively this is Nn0, and effectively that this one here is effectively dominated by delta P, that's what I'm saying. I could roughly say that this is beta N0 times delta P, or delta N, they are the same. Remember, I won't now argue on that. Plus, sorry, when you do that, there is also an additional term here. It's better if I do that because otherwise you won't. Let me do this step. So this is beta Nn0 plus delta N Nn0, sorry, P N0 plus delta P. And so now, obviously, I have a lot of products here. The interesting is to keep the interesting bits. So one interesting is that is meaningful is this with this, because this is big, this is big. So beta Nn0 delta P. And another term that is interesting is this one with this one, because this makes this term here. So plus, so I will mark, which one did I say? This one with this one. The rest is effectively, sorry, negligible. So this term here is actually what we called the thermodynamic equilibrium recombination rate, and we baptize this U. U is the net recombination rate. So there is always a recombination rate due to temperature, that is the one required to maintain thermodynamic equilibrium, to maintain this situation. But if the system goes out of equilibrium, there is an extra effort, effectively, that needs to be put in place. And this is what U represents. We can, from what, so this, the equation we've written just now is R equal R which we can write U equal R minus. That's what we said in words. And it's nice to see it in this way. R was defined as this, and R thermodynamic equilibrium was defined as that. So we can effectively, or remember that N and 0, P and 0 is Ni squared. So allow me to write it like that, this one. So effectively, in the end, U is beta Pn times Nn minus Ni squared. So here clearly we see the out of equilibrium contribution. So this is if this is different from 0, means we are out of equilibrium. But I've done this step here to show you the net recombination rate written like that, because this is telling us something also even more interesting. If this quantity is positive, that is Pn and N is bigger than Ni squared, so we have injected the extra carriers, this means that indeed I need to recombine more. This means that there is a true positive recombination rate required to bring the system down to equilibrium. But if this quantity is negative, the net recombination rate actually becomes a net generation rate, because this quantity becomes negative. A negative recombination means effectively generation. It's the opposite, isn't it? So that's quite interesting, how the system is always trying to keep itself toward equilibrium. Now, so I will remove some of this stuff here. Done that. Let's remove this one here. So now, using a similar approach to what we've done for R, you see R, in the end we've demonstrated R is the thermal equilibrium component plus the net recombination rate, which is extra. So the same we can do for G. In general, G, so if I go now here, this diagram here is for a situation where we have an agent that is causing extra carriers, light. In that case, you see the light is causing GL, so an extra generation rate of electrons and hole pairs. On top of that, you have still the thermal generation rate. And so, and then there is R, which we have just dealt with. So clearly from this, we can realize that G will be similarly to what we did for R. So this is the term related to thermodynamic equilibrium plus the external source. Or remember, the units are always, for this quantity, is number of generation events of electron hole pairs generated per cubic centimeter per second. Okay, so in my system now, in my semiconductor, I have some external agent, light, that is causing generation of extra electron hole pairs. And at the same time, I have recombination that is trying to create equilibrium. So at any moment in time, remember that, as we said, of the two type of carriers in this end semiconductor, what is worth looking at is the minority carrier. So we are kind of focusing now our attention to the minority carriers because these are more affected in terms of their density is more affected. So what I could, remember these are rates per second. So I could write this equation. In general, the variation in time of the minority carrier density is equal to the difference between how many are generated per second per unit volume and how many are recombined per unit second per unit volume. It sounds quite, if this is bigger than that, it means that the density of minority carrier will be increasing in time. That's what this is saying. If this is bigger than that, this whole quantity is negative, this means that I'm decreasing the number in time, I'm decreasing the number of minority carriers. That makes sense, isn't it? Okay. So remember that G, we can further expand this based on what we just said. R is this. We've said that G, T thermodynamic equilibrium is equal to this, so effectively I can cancel out these two. So in the end, I'm left with this equation. That is, the variation in time of the minority carriers is related only to those generation recombination rates that are extra to those related just to the thermodynamic equilibrium. The net recombination rate and the external agent that is in this case, let's say light. And at this point, let us assume that we are shining light on this semiconductor. Let us assume that we've done that for enough long time that the system has reached steady state, which means that basically this derivative is now zero. Whatever was change was happening, enough time has passed so that the system is now stable. So I'm at steady state. Which is this quantity equals 0, means that G, L minus U must be 0. And so GL must be equal to U. Oh, we did call this U. I forgot about that. So, and so this was U, remember? And so we have this beta n 0 time delta P. Remember, delta P is defined as Pn minus Pn0, so the out of equilibrium value minus Pn0. So I could rewrite this quantity as beta nm0 time Pn minus Pn0. Now, these quantities are recombination or generation rates, a number per unit volume per unit second. This is a density of carriers, a number per unit volume. So this is the inverse of time, must be, to match the units. Effectively, this means that, if you allow me to go somewhere else, maybe here, this quantity here is 1 over tau p, is the inverse of some time. So we can define, we are defining here, sorry. So we can define here the lifetime of minority carriers as 1 over beta nn0. And so we can write, so this is the lifetime of minority carriers in my n semiconductor. And so we have that U, which is also equal to GL, becomes in general Pn minus Pn0 over tau p. So we clearly see here now that this net recombination rate is linked to something more practical, suddenly, that is the lifetime, something that probably we as a physicist are more familiar with, the lifetime of the carriers. How long they live before they recombine. That's what this time is telling us. Yeah? What is funny to note is that this lifetime is inversely proportional to the density of the majority carriers. So the more majority carriers I have, the less the minority carriers will live, because they will recombine more quickly. That's what this is suggesting. And so if in other words, if nn0 increases, tau p goes down, and so U, the net recombination rate, goes up. This is the chain of conclusions I can get from all this. So this is in few steps, and with some simple considerations, the theory of generation recombination carriers in the direct recombination. And we end up effectively, there is no reason to write down these things. You can, let me show you you will get these notes anyway. So we can write, so we've done this for the P, for the minority carriers in an N semiconductor, which is the top equation there. So for an N-type semiconductor, we can write that equation there. If it was a P-type, for the corresponding minority carriers, which are obviously electrons in that case, we write the second equation. Okay, so this is somehow summarizing the whole thing. Now, I have on this is a very nice generation recombination. As you can see, we start playing with light now. And so now you can start thinking to some nice applications of semiconductors in more real life. I have here an application that I will not do here because it will be, take too much time, but I will do it in the post-lecture video. It's an example of how to apply this to make what we would call the first sensor we've ever dealt with. So make a photoconductor. Okay, so with this kind of story, this kind of equations, you can quickly realize how a semiconductor can be turned into a sensor, a photoconductor. Okay, I'll leave this for later. And just before I stop for the break, I will tell you. So we've dealt with the direct recombination process. We said that there is also the indirect recombination process, and that passes through the presence of some defects, and those are involved in the recombination of the electron and hole pair. The theory is quite complex, and it's called Shockley-Reed-Hall recombination theory. and you will see it in my notes. I'm just mentioning it as a curiosity and just for you to know, indirect recombination. The equation is extremely, you see U here is extremely more complex because we are involving now another object in the story, a trap, a defect. So, but the funny thing is that in the end, and this is what I wanted to tell you, in the end, if you do some simplifications, you can actually write U in this term again. The only thing that changes then is the final expression for the lifetime, which depends then on the defect cross-section, and the thermal velocity of the carriers in the semiconductor, and the density of these traps, these defects. But what is nice is that in the end, even this thing that seems quite complex kind of falls into the same story or analytical approach. And finally, just again to make you aware of this, so direct recombination, indirect recombination, surface recombination. The surface of a semiconductor, beyond the surface, there is nothing. So all the bonds that those atoms that are on the surface were willing to do with the neighboring atoms can't do these bonds because there is nothing. So the surface is full of dangling bonds. These are effectively defects, are places where, you know, the imperfections for our crystal. And so there is also another recombination there that someone could consider, which is called surface recombination, and also there you end up with something similar to this. The only thing is that instead of having, you see, this is the term that is equivalent to that, Pn minus Pn0. The only thing is that this is the density on the surface. Time here, this is a velocity actually. This has to do with the dimensions of these quantities in the end. But just I think out of curiosity, it's good that you know that there are, you know, recombination is quite a complex thing. We will be dealing mainly with the direct one, which is the simplest one and most meaningful for us. But the subject is quite more vast than that. Okay, let's have a break now. We start at 3 o'clock. I just realized that I did not. Okay, so there may be. I did not. So if you watch the video, there is all this bit that you won't be able to see.